problem that we're going to start with here, this comes from last semester, and it was on the first exam. And students did not like it very much, but that's okay. They grow to like these problems. Sort of like Stockholm Syndrome. I don't know if you're familiar with it, but the longer you stick around, the more you enjoy these things. All right. So find the value, or possibly values, for A, so that the two surfaces, x squared plus y squared plus z squared plus 1 equals a squared plus 2z, and x squared plus 4a squared plus y squared plus z squared equals 4ax plus 2z, intersect in a single point. Now, of course, there's some obfuscation here, because there's this word surfaces. We are going to learn about more surfaces. What surface have we learned about already, though? Spheres. And it turns out these are spheres. What's the giveaway? Well, the fact that when you see x squared and y squared and z squared, all the same coefficient, all on the same side, that's going to be a sphere for us. That's the only kind of thing that has that. So if we think sphere, we put our sphere hats on. We say, well, let's put all the variables to one side. So for example, let's start with this first equation. X squared plus y squared plus z squared minus 2z. I'm moving this across. I'll leave the plus 1. It looks pretty harmless there. Equals a squared. Now this z squared minus 2z plus 1 happens to be very nice. What is it? Z minus 1 quantity squared. It's a perfect square. All right. So our first surface is a sphere. And in fact, we can say more about it. And we will in a moment. Let's do our other one. So we'll change colors slightly for our other one. So for our other one, let's move the 4ax across. So I have x squared minus 4ax plus 4a squared plus y squared plus z squared. I'll move the 2z across. Minus 2z equals currently 0. Now, if I look here, what can I do? It factors. In fact, this is a perfect square. It's x minus 2a quantity squared. And you can check. If you divide 4a by 2 and square it, you get 4a squared. Okay, y squared is fine. Now here, we don't have a perfect square. Not yet. But what can we do? Plus 1. Plus 1. Now I can't just add 1 here without balancing it. There has to be a balance. So I could subtract 1 right away, but generally speaking, I like to do the same thing to both sides. So I'll add 1 on the other side. So this becomes z minus 1 squared equals 1, or 1 squared. And I'll write it that way because I'm anticipating that I want to think about what we have. So we have one sphere which has center 0, 0, 1 and radius a. That's the first equation. Wait a second. I just lied to you. Do we know it has radius a? Well, we have to be careful. What are we told about a?
Nothing.
We're told nothing about a. So a could be negative. Could I have a negative radius? No. So I'm going to be careful and hedge my bets and say my radius is absolute value of a. All right. So now the first, that's the first. The second, 2a, 0, 1. What's my radius? 1. You're probably getting nervous. Is it absolute value of 1? No, just 1. 1's a number. Okay. So now I have the centers and I have the radiuses. By the way, we did not actually enforce you had to know the absolute value. That's just, I don't want to mislead you. So now we say, okay, what comes next? We want them to intersect in a single point. So we have to start thinking, what does it mean for two things to intersect in a single point? If you have a hard time thinking three-dimensionally, go down. Think two-dimensionally. If I have spheres, that's my three-dimensional thing. What's my two-dimensional thing? Circles. So, how can I have two circles touch at a single point? Well, one way is I could do something like this. They don't have to be the same size. One could be bigger. So that's certainly true. Is there any other way? It is possible that one could be inside the other. And that's a slightly different scenario. So let's think about both of these options. Okay, so let's do the first setting. Okay, so we have them touching. Well, let's think about what that means. How would I know if they just barely touch? Well, one nice thing is I can think about the distance between the centers. And if I think about the distance between the centers of two circles which just barely touch, what must be true about that distance?
Sum of the radii?
It's the sum of the radii. And it turns out in 3D, same thing. So let's think about the distance between these pairs of points. So because the z-coordinate matches and the y-coordinate matches, the distance is the difference in the x-coordinates. So if I think about the difference in the distance, that's size of absolute value of 2a. Again, I say absolute value because a could be negative. Well, that has to equal the sum of the radii, which is 1 plus absolute value of a. So then we get 2 absolute value of a equals 1 plus absolute value of a, because when you have absolute value, you can pull constants out, just make sure they come out positive. And we move that across, we end up with absolute value of a equals 1, which tells us that a is either plus or minus 1. So those are some values for a. So we know it works for at least two values, 1 or negative 1. All right, well, that's one thing that could happen. What's something else that could happen? Well, in this picture, what's true? What's true about the distance between the centers?
The bigger radius means the smaller.
Yeah, the difference between the centers is the absolute value of the difference between the radii. So on one case, you add the radii. And radii, by the way, in case you're wondering what does radii mean, it's plural for radius. It's sort of like octopuses. You know, the plural for octopuses is octopuses. It's not octopi. But anyways, that's why I'm saying radii. Okay, now, so the difference between the centers is the difference between the radii. Oh, now it gets interesting. Okay, absolute value inside an absolute value. Just what you want to do on a Monday. Wait, it's a Wednesday. Yeah, you want to do this on a Wednesday. You've been thinking. Okay, good. Well, there's two possibilities here. First off, I can still pull the 2 out, which is that the absolute value does nothing, which would say 2 absolute value of a equals 1 minus absolute value of a. Or it could be that the absolute value flips a sign. So 2 absolute value of a equals absolute value of a minus 1. That would be if I flip the sign. Now let's think about this case for a second. If this were true, what would I write next? And pull that across. What would I be left with? Absolute value of a equals? Negative 1. Wah, wah, wah. Can't happen. Okay, no solution going down that road, but that's okay. We have another chance. Oh, sorry. There's a frowny face there. Okay, how about over here? What happens? Well, add 3 absolute value of a equals 1, or absolute value of a equals 1/3, or we can conclude a equals plus or minus 1/3. And therefore, it's plus or minus 1 or plus or minus 1/3. Not so bad. Not so bad, but you have to think. Now, this idea of if you have a hard time thinking three-dimensionally, try to think two-dimensionally. It's actually a very useful tool. Analogy is a very powerful tool in mathematics. And so if you're stuck, just try to think, is there a simpler case? when you're in 3 dimensions, the simpler case is 2 dimensions. So it's a way that you can help get unstuck. So for today, we're going to keep building up our geometrical intuition, and we're going to talk about different coordinate systems. So let's do coordinate systems. Now, we talked about a type of coordinate system last time, and it's called the Cartesian coordinate system. But it's not the only coordinate system out there. So Cartesian, the way it works is it measures everything in terms of distances. So in particular, when we're talking about a Cartesian coordinate system, we have a pair of distances. Usually we say x and y. So it's a distance we move in a direction we call the x direction, plus a distance we move in a direction we call the y direction, and that gives us our location. So in other words, if we want to know where we are, we start from a fixed point, which we call the origin. We move in the x direction, then we make a right turn, and we move in the y direction, some prescribed amount. But it's not the only way we can describe where we're at. Now there's another coordinate system that we saw in last semester in Calculus 2, which is called polar. Now polar works a little bit differently. It uses a direction and a distance. So it's not a distance plus a distance, it's a direction plus a distance. And the idea is you start from the origin and you rotate. So I'm at the origin and I rotate some amount. And then after I've rotated, I move forward some amount. So there's an angle, which tells you the direction, and there's a distance that we call r. Tells you how far out to move from the center. So that's polar. Now, where do you see polar? It actually shows up in a lot of places. And in fact, in some sense, it's a very intuitive thing if I want to say, what's happening relative to me? So suppose, for example, you're on a ship in the middle of a large body of water. Well, what you can do is you can say, where are the other ships located relative to me? So you might see this in old wartime films where they'd have this spinning antenna. It was a radar. And what it was doing was sensing where is everything located to me. And then you'd have people in a dark room, young little guy, very thick glasses, staring at a screen, and there's a thing, boop, boop. Have you ever seen those films? Sometimes they use it also in science fiction, and it's like, it's 4 meters away, and it's like, it's 2 meters, it's right on top of you, But it's that same philosophy. Where are you relative to me? All right. So how do we go back and forth between these two systems? The way to figure that out is just put the coordinate systems right on top of each other. So I can say, hey, there's this picture that involves x and y and r and theta. And what you see is that it's a triangle. In fact, it's the right kind of triangle, our favorite kind, because trigonometry is built off of right triangles. So then we have a couple of nice facts about right triangles. For instance, we can say x squared plus y squared equals r squared. Pythagorean theorem, powerful theorem. All right, and that makes sense. Because if you say, well, r is how far out your point is, well, my point xy versus my point 0, 0, the distance formula would say square root of x squared plus y squared. That matches this formula. I can also look at trig functions. So for example, cosine theta, well, that's the ratio of adjacent to hypotenuse, x to r. Well, if I solve for x, I get x is r cosine theta. Similarly, I can say sine of theta is my opposite over my hypotenuse. Opposite over hypotenuse is y over r. Y equals r sine theta. And I can even say tangent of theta equals y over x. Now you might say, Steve, you're off your game. This is an excellent opportunity for you to say theta is arctangent of y over x. You're passing up an opportunity for an arctangent? That's unlike you. You have to be careful though, because it's true that tangent of theta is y over x. It's not true that theta is arctangent of y over x. Can you see why there'd be a problem?
Doesn't arc tangent go between negative pi over 2 and pi over 2?
Yeah, arc tangent is limited. It can only go between negative pi over 2 and pi over 2. But you might actually end up with a theta that is not between negative pi over 2 and pi over 2. So that's why you have to be careful. That's why, for this brief time, we will pass up on the arc tangent. All right. Now, why do we have different coordinate systems? Well, it can be the case that changing coordinate systems can help simplify the curves that you're looking at and any relationships that you might see. So we're going to do an example here. Let's sketch all points which satisfy the following. X squared plus y, all of that quantity squared, is equal to x squared plus y squared. How hard could that be? Well, I would say if I just saw this expression in terms of x and y, I'd have a hard time doing this. But given the context that we just talked about switching coordinate systems, I suspect perhaps it'd be a good idea to switch coordinate systems. So let's see what happens if we do. Okay, so let's see, what can we do? Well, I see some x squared plus y squareds. What can I do with those? Turn them into r squareds. So I have an r squared equal something else, r squared. What about the y? R sine theta. Okay. Now, both sides are squared. Okay. Get rid of the square. Square root. So, r squared plus r sine theta is equal to r. Now what? Divide by r. R plus sine of theta equals 1. Another way you could write this is r equals 1 minus sine theta. Now, when I write in terms of x and y, it's pretty complicated. When I write in terms of r and theta, it's less complicated. I don't want to claim it's trivial, but it's certainly more manageable. There's a lot less going on, and we have a better shot. So if I think about r equals 1 minus sine theta, quick flashback to Calc 2, well, what I can do is I can sort of say, well, what are some key points? Well, what's the biggest sine theta could be? 1, and that would happen at pi halves. And so I know at pi halves it would just barely touch the origin because I'd have 1 minus 1, which is 0. So at pi halves I'd be right at the origin. At, say, theta equals 0, sine of 0, 0. So it'd be out distance 1. Similar with pi. Sine of pi is 1. How about down this direction, 3 pi halves? How far out would I be? You'd be out 2, right? So if you were to go through and plot this, you'd get something that starts out, gets closer, then grows, gets bigger, and then comes back around. And this has a name. It's a cardioid. And it's a way you can, if you're mathematically inclined, you can pass along messages. Of course, we all know the real message here is that we love 265. It's our favorite class. Our favorite class. When I was a young person, this is college had a newspaper, and for Valentine's Day you could print a little tiny Valentines for a small nominal fee. And so I did that for my girlfriend. R equals 1 minus sine theta u. Yeah. This was back before we had emojis, so, nowadays you don't need that. Okay, so that's two-dimensional coordinate systems. How about three-dimensional coordinate systems? And there's 3 of them that will show up. Now, when I say they'll show up, let me be clear that for the majority of the semester, a vast majority, we're going to be dealing with the Cartesian coordinate system. That's the Cartesian coordinate system we talked about last time, where we had x and y and z, where x is the distance you go in the x direction, y is the distance you go in the y direction, and z is the distance you go in the z direction. So here the Cartesian coordinate system is based off of distances. How far do I go in each direction? But you can think about polar. Polar says, let's combine direction and distance. Sorry, I keep messing up. I should have said Cartesian is just about distances. All right, so how do we get there? Well, we can sort of compromise and think about cylindrical as sort of halfway in between. So the way you should think about cylindrical is that this is really the polar coordinate system plus z. So in other words, in cylindrical, you say, let's first find where you're at in the xy plane. So I'm in the xy plane. I start at the origin. I turn theta. I move out distance r. And then, that's where I'm at in the xy plane. I move up and down vertically according to z. So that's how I'm going to find where I'm at. So the theta that you see here in cylindrical is the same theta that you see in polar, because it's truly building off of polar. Now, you might say, well, that's sort of a halfway. Let's go more pure. A true thing where we say a direction and a distance. And the way we're going to do that is what's called spherical coordinate system. And the spherical coordinate system involves two directions. And by direction, I'm talking about angles and one distance. Now the distance is this character here. It's called rho. One of the nice things about learning mathematics is you really get to brush up on your Greek alphabet. So that's rho. And so rho is how far you are from the origin. But now I have to know, well, what direction do I do to get there? So here's how you do it. You start, let's say I'm at the origin. And first I rotate an angle theta. And then I have to do my up-down direction, and that's phi. Now we have to be a little bit careful. Intuitively you say, well, let's do phi off of the xy plane, but we're not going to. So phi, it's noted here, it's off the positive z-axis. So in other words, I'm going to have phi coming off the positive z-axis. So phi equals 0 points straight up. Phi equals pi points straight down. And I never need to go outside of that range between 0 and pi. Now, suppose I were in the xy plane. What would phi be? Now you're probably thinking, well, Phoebe is a character from Friends. No. So what angle would I be with the z-axis? What angle do I form? Pi over 2. You form a 90-degree angle. So the xy plane, the whole xy plane, is when phi equals pi over 2. So the reason why we want to go off the z-axis is because it's really quite simple. Because when you have the z-axis, phi equals 0 is the z-axis going up. Phi equals pi is the z-axis going down. All right, well, I think I should comment here that depending on what type of engineer you are, you might see spherical coordinate systems where they switch the roles of phi and theta. I apologize. I don't know who did that to you. That was a mean prank. But this is the correct way, I guess. Another side note about spherical, in case you're thinking, okay, what's some intuition? How can I relate to spherical? Think about Star Trek. Now, if you think about when they talked about, I want to go to a certain destination, how did they tell, their pilot? How do I get there? Well, they'd say, heading 240 Mark 172. Well, what was that? The 240 is an angle. Mark says, now I'm ready for the next angle, 172, the second angle. So what was happening was they were saying, here's the direction to go. And then, of course, engage. Now you start moving in that direction. So that's what's happening. We say the direction, and then we move forward. Now, down below here, I have a couple of empty spaces. I just want to talk about what happens in these different coordinate systems. So in particular, I want to talk about what happens if I fix a single coordinate. So let's go through and think about what we have. So I'll start with Cartesian, because that's the one we know best. Suppose I look at x equals a. And I say, if I fix x to be a particular value, what do I get? What's the shape? So I want all the points where x equals a. What do I end up seeing? A what? A plane. Yes. So the x direction is coming out. So I'll mark the coordinates as we do in our coordinate system. So I come out to A, and it turns out it's all these points here. So x equals A is a plane. What if I fix not the x coordinate, but I fix the y coordinate? Y equals something else. Let's say y equals b. Then what do I see? I still see a plane. But what happens now is I go out in the y direction to some distance b, and I look at all the points which have value b. Well, process of elimination, you probably can guess what's coming up next. The z coordinate. What happens there? It's still plane. These are plain and simple things. So, what do you see? Well, what you have here is that when you're working with Cartesian coordinates, it's really wonderful for boxes. We love boxes. We could call it the box coordinate system. Now, you might say, well, that's fantastic, because boxes are very easy to do things like, for example, compute volumes. And so we're going to see this coming back in the third part of our course. Okay, so that was Cartesian. Let's talk about cylindrical. Are any of these three variables, or rather parameters, theta, r, and z, are any of them easy to figure out what happens? Z. Now the reason I say z is the z that you see in Cartesian is the same z that you see in cylindrical. So in both cases, z measures how far up you go from the xy plane. So whatever z does in Cartesian, you see the same thing happening in cylindrical. So what do you get? You get the same shape. It's a plane. All right. Well, how about theta? Suppose I fix theta. What would I see? So theta being fixed to some angle. Well, what? I would have a plane. And so what I do is, you can think of it in the following way. Start in the xy plane, and I go some direction here where this angle is alpha. Now, when I say theta equals alpha, you might notice I make no restriction on z. I make no restriction on r. So the result will be all the points where I have alpha. And what you get is you get actually something a little bit less than a plane. You get a half plane. And the reason I say a half plane is because that angle coming out on the other side is an alpha. It's a different angle. Of course, that assumption is based off of r being positive, which I think is okay for us to assume. Now, what about r? Suppose I fix r to be something, let's say tau. So r is fixed. What would that look like? It would be a cylinder. Now, think about r in just polar coordinates. Build your intuition up there. If I said r equals 2, you'd have what in the xy plane? Circle with radius 2. Now when I go to cylindrical coordinates, I say r equals 2, well I still have a circle in the xy plane. But what happens is, regardless of z, I still see that same circle. So it's that same circle getting copied up and down the whole way. So what ends up happening is that you see a cylinder. Now, you might wonder, where did cylindrical coordinates get its name from? Well, look, it's got a cylinder right there. Hence cylindrical coordinates. And in fact, that's not just a coincidence. That's a reason why. But more generally speaking, what are cylindrical coordinates good for? The answer is that they're great for rotational symmetry. Now, what do I mean by rotational symmetry? In other words, whoops, let me move that up a little bit. Whenever I have some rotation, some symmetry around the z-axis, so you imagine that you're spinning, like you have forming like a clay pot, or maybe you're doing some woodwork. You have it on a lathe. But if you can spin it around the z-axis, and that spinning leaves the shape alone, that's the symmetry. And there are a lot of times when we actually do have shapes which have that nice symmetry. Okay, spherical coordinates. Well, is there anything that we know already?
The R.
Well, we have three things: theta, phi, and rho. And the answer is theta. Why? Because the theta in cylindrical coordinates is the same as the theta for spherical coordinates. They have the same properties. So again, I see these half planes coming out. So this is my theta equals alpha. Okay, so that's the same. What about rho? Let's talk about rho. Suppose I look at something of the form rho equals tau. What would I have? What? I'll give you a hint. It's a sphere. So what's rho? Rho is the distance from the center, which is the origin. So I'm looking for all points which are a fixed distance, in this case tau, from your center. So that's the definition of a sphere, is you look at all the points which are a given distance away from your center. So you can describe spheres very nicely inside of spherical coordinates, and hence the name spherical coordinates. Okay, well, that leaves us with one more thing, which is our phi. So, phi equals beta. What does that look like? Well, notice that if I come to this picture here, on this segment here, they all have the same phi. They're all coming off at the same angle from that z-axis. So every single point on this line here has the same angle. And again, I can spin now with respect to theta, because theta and phi are independent. And I'm still going to get points with the same phi. So the result here, if I can imagine spinning this segment around, the shape is a cone. And the angle that comes off is this angle beta. All right, so that's spherical. So what is this good for? Well, it's great for spheres. All right, well, it's also great for anything where you have symmetry about the origin. And we'll encounter a few situations like this later in the course. Okay, well, I have three coordinate systems. And in each case, what happens here is I'm just describing ways to say, where am I? Now, keep in mind that different coordinate systems are not different spaces. It's always the same space. I'm always in this three-dimensional space. I'm just describing things differently. So you might say, well, can I go back and forth? In other words, is it easy to transition from one coordinate system to another coordinate system? And the answer is yes. And what you do is you take your three coordinate systems and you just put them down right on top of each other. So what I've done here is I've taken the three pictures and I've just merged them all together, because I was always doing the same point. And then you can see a couple of things happening. Well, for instance, down here I have the xy plane. And if I'm in the xy plane, I can say, hey, this x, y, r, and theta do the same thing as they did before. So I still have these relationships that come from polar coordinates. So in other words, x equals r cosine theta, y equals r sine theta, r squared equals x squared plus y squared. That gets inherited. Okay, well that's not so bad. What about the next equation? Rho squared equals x squared plus y squared plus z squared. Well, what's that? Well, what's happening is I'm measuring the distance, rho, and I'm saying, well, how far out is it? And so I remember from last time that if I have a point, I can think of this point in Cartesian coordinates as x, y, z, and I'm going from 0, 0, 0, well, that this distance, rho, is the square root of x minus 0 squared plus y minus 0 squared plus z minus 0 squared. So this bottom equation, rho, that's the distance formula. Okay, well that's not so bad. How about the next two? Well, the next two follow from noting that I have here a right triangle. On one side I have r, another side I have z, on the third side I have rho. Now the only thing I don't have is an angle, but I do know a couple of things. This angle phi here, it turns out that this angle down here, it complements it. In other words, this angle says, hey phi, you're looking pretty good today. That's what a complementary angle is. So, pi halves minus phi. Well, but this angle up here, it complements that angle. So what can I say about this angle up here? It's phi. Now what I have is I have a right triangle, and I can do the same trick I did when we talked about the polar coordinates. So, for instance, I can say that the ratio of the adjacent to the hypotenuse, z divided by rho, is cosine phi. So that becomes z equals rho cosine phi. The opposite, so opposite over hypotenuse, r over rho is sine phi, so r equals rho sine phi. So this is trig. And then you get to two obscure ones. And when I say obscure, I don't memorize these. X equals rho sine phi cosine theta, y equals rho sine phi sine theta. The reason I don't memorize them is I can recover from what I have in the rest. Why do I say that? Well, what is x? X is r cosine theta, because it says x equals r cosine theta. What is r? Rho sine phi. So x equals r cosine theta becomes x equals rho sine phi cosine theta. Okay, so this is sort of a combo. You can get this from doing the rest. All right, so when it comes to knowing the formulas, I would say you don't really need to remember the combos, but you should remember the other ones. But they're not so bad. Polar we already committed to memory from last semester. Distance, that's not bad. Trig, we like trig. All right, example. Suppose you have this point 1, 1, root 6. So this is Cartesian coordinates. By the way, Cartesian coordinates is the only time we list things as number, number, number. For spherical coordinates and for cylindrical coordinates, we don't have that convention. We just say, well, we're at theta equals this, and r equals this, and z equals that. So I have this point here, and I want to write it in terms of cylindrical and spherical. Let's start with cylindrical, because it says cylindrical first. That's as good a reason as any to start with cylindrical. So for cylindrical, I have three numbers. I have r, theta, and z. Are any of these going to be there for free? Z will be free because this is x, y, z. And z in cylindrical and spherical, cylindrical and Cartesian are the same. It's a freebie. Woohoo! Root 6. Now, as far as r and theta, I can now go back into the xy plane because cylindrical coordinates is polar plus z. So now let's do the polar part. I have a point here, 1, 1. What's my angle theta? Pi fourths, because I'm forming a 45-degree angle or a pi fourths angle. What's the distance from 0, 0 to 1, 1? Square root of 2, because 1 squared plus 1 squared, take the square root. And we're done. I've now taken this point, 1, 1 root 6 in Cartesian, and said in terms of cylindrical, you go r equals root 2, theta equals pi fourths, z equals root 6. Well, that's half. Let's do the other half. Spherical. Well, for spherical, we have theta and phi and rho. Okay, are any of these going to be for free? Theta will be for free. 1/4 pi. All right. Well, let's try one that's not quite for free. What's probably the next easy one? Rho. Rho is not going to be bad because of our formula. We have that rho squared is equal to x squared, which is 1, plus y squared, which is 1, plus z squared, which is 6, which adds up to 8. So that's rho squared. What will rho be? 2 square root 2. Good. Okay, so that's rho. What's left? Phi. Well, how do we get phi? Well, probably the easiest thing is to come over here, use some trig. All right, I would suggest in particular the top one, because I already know z and I already know rho. Doesn't matter, we could use the bottom because we computed r as well. Okay, so what do we have? We have that cosine phi is equal to z divided by rho, which is equal to square root of 6 divided by 2 times square root of 2. Oh, this looks like fun. What do? You multiply top and bottom by square root of 2 over square root of 2. And simplify. Upstairs you have square root of 12. Another name for square root of 12? It becomes 2 root 3 because it's square root of 12 has 4 times 3. So that's 2 square root of 3. Downstairs, what do you get? You get 4, 2 times 2. You can cancel some 2's. Square root of 3 over 2. So cosine of phi is equal to square root of 3 over 2. Do we know an angle where cosine of phi is square root of 3 over 2? Pi over 6. Is there any other possibility for phi? And the answer is no. Because phi is always going to be between 0 and pi, and it's always going to be unique. There's not going to be like, oh, there's 2 possibilities for this number. There is not. So pi over 6, that's how far off we come off. And we're done. That wasn't so bad. All right. Well, one of the things to do to get some intuition is to look at some common surfaces. So surfaces which we will encounter at points throughout the semester. Spheres, cylinders, and cones. So a sphere of radius tau, centered at the origin. Some of these things should not be surprising because the first one is from last time. X squared plus y squared plus z squared equals tau squared. This top one, that's Cartesian. The next one, what do we do? Well, x squared plus y squared is r squared. So r squared plus z squared equals tau squared. And then the bottom one, we've already talked about, if I wanted to describe a sphere, is rho equals tau. Okay, so that's not so bad. All right, what if I want to have a cylinder of radius tau where I'm centered on the z-axis? So again, the picture, my z-axis, that's the part going straight up and down, and I have some cylinder where if I were to look where the center of that cylinder is, it's right in the z-axis. Okay, how do I describe it? Well, we've already talked about in our cylindrical coordinates, r equals tau. By the way, if I just pointed to this and I said, what coordinate system is this? Could you figure it out if I just said, hey, what coordinate system am I in if I say r equals tau? And I'm in 3D. I guess I should add that in. You look at what variables are being used. If you're only using x, y, and z, so I should say if you have an x or a y, you've got to be in Cartesian, because that's the only one that uses x or y. If you have an r, you have to be in cylindrical, because that's the only one that uses cylindrical. But then, of course, you look for combinations. If I have both r and z, I have to be in cylindrical. So you look at what variables are being used. Now, this one looks really weird. The moral is, some things get simpler, some things get more complicated. Rho equals tau times cosecant phi. Where did that come from? Well, if you come back to what r is rho sine phi. So if I want rho to be tau, I have that tau would be equal to rho sine phi. And now if I solve for rho, I move the sine phi across. Well, what happens when I move the sine phi across? What does it become? It becomes cosecant. All right. And then if I want a cone, and a cone has this type of shape, what do I want? Well, in spherical coordinates, that's a very nice, easy to describe cone. In particular, you'll see, because I say it forms an angle of pi/4 with the z-axis. So when you see that, oh, forming an angle with the z-axis, that's phi. Phi does that. So phi equals pi/4. Then, where does the other ones come from? Well, z equals r. Okay. Why is that? Well, if you look at this, if you start with your equations here, you can actually say that z over, oh, whoops, no, let me get this right. If I do r over z, if I divide r by z, what do I get? Well, rho sine phi divided by rho cosine phi, what is that? It's just tangent phi. So you get that r is equal to z times tangent phi. The rho's cancel. And if I know phi equals pi/4, tangent of pi/4 is 1. So you get r equals z or z equals r. Generally speaking, if you have z equals a multiple of r, then what you have there is you have some type of a cone. And z equals square root of x squared plus y squared, well, that just becomes from that r equals the square root of x squared plus y squared. And in my last 60 seconds, speed run. Okay, identify and sketch rho equals 6 cosine phi. Now the problem is 6 cosine phi is hard, but rho cosine phi is easy, so multiply by rho. What is rho cosine phi? Hopefully you took notes. It's z. So you get x squared plus y squared plus z squared equals 6z. So you move the 6z across, leave a suspicious gap. How do you finish? You add 9. And lo and behold, what kind of shape do we have? It's a sphere. Can you tell me anything about this sphere?
It's centered on the origin.
Centered up at 0, 0, 3 and radius of 3. So it's a sphere that's sitting on the xy plane. All right. We'll stop there for today and pick up next time.